Hello everyone, hello lovely students, welcome back to this video session. Hope you all are doing great in your life. My name is Ashwant and I'm from India, which happens to be a very awesome, wonderful country. And today I have got a really exciting math lesson for you all. Want to know what's that? Then please don't skip and make sure to stay with me all around till the end. Here we go. A simple expression fx is equals to the square root of x minus 3. And at the same time, let us take one more expression, gx is equals to 1 upon square root of x minus 3. Now, we want to find the domain for both these expressions. As we all know, domain is set of all the values of the variable in the functional expression for which the functional expression generates a meaningful output. Okay, now what is this? Let's understand. If we observe fx is equals to square root of x minus 3, let's take some values for x. If we take x is equals to 4, we get 4 minus 3 square root of 1. It is defined. Okay, this expression is defined if we take x is equals to 4. If we take x is equals to 5, we have 5 minus 3 square root of 2. Again, it is defined. Let's take some non-integral values. If I write 7.2, okay, again we have 7.2 minus 3. It is 4.2. It is defined. What if I take x is equals to 3? So we have 3 minus 3 square root of 0. Again, it is defined. Now if I take x is equals to 2, what happens now? So 2 minus 3 is equals to square root of minus 1. It is not defined. So in our earlier classes, we all have studied like whenever we have a square root sign, then whatever is written inside the square root sign, it has to be either positive or it has to be 0 if we want the square root expression to be defined. So I can conclude that if we want this fx square root of x minus 3 to be defined, then this x minus 3, okay, better I should write like we have fx is equals to square root of something. You know, this structure is similar to this. Fx is equals to square root of something. So if we want our fx, this functional expression, to be defined, then we have to make sure that something is greater than or equals to 0. Okay, now if we solve this inequality, something greater than or equals to 0, this will give us the domain. Okay, domain, it will give us domain means the collection of all those values of the variable x for which our fx is defined. So you have to remember this, you have to memorize this. Okay, you have to memorize this. You all memorize this. Now, let's have a look at this. When we have 1 upon square root of x minus 3, now what is the difference between these two? See, again we have a square root sign, but unlike this situation where we have a square root sign in the numerator, here we have square root sign in the denominator. Okay, so if I take x as 4, 1 upon square root of 1, it is defined. If I take x as 5, that is defined. Now, if I take x as 3, it is not defined. But in this case, you know, just I want to recall you, here it is defined when we take x is equals to 3, because in this situation the square root function was in the numerator. Okay, but in this situation when we have a square root function in the denominator, then we cannot give it a 0 value because 0, when we have 0 under the square root sign, then this square root is defined, but the overall expression is not defined because denominator cannot be 0 in maths, because division by 0 is not defined. So when we have this type of structure, what is this structure? I'll write it for you. We have gx is equals to 1 upon square root of something. Okay, so in this case, when we have a square root function in the denominator, then our condition will be something greater than 0. I want you all to understand the difference. Okay, so when we have fx is equals to square root of something, we have the condition something greater than equals to 0. But when we have an expression of this type 1 upon square root of something, when the square root of something is in the denominator, then we are not supposed to use the equality sign. Only greater than 0 is sufficient here. Okay, I hope you all understand. So if you are able to understand this, now you can easily find the domain for both of these expressions, isn't it? So for this fx, x square root of x minus 3, and for gx 1 upon square root of x minus 3, what you can write here is, for domain of square root of x minus 3, simple something, this is your something, it has to be greater than equals to 0, and when we have 1 upon square root of x minus 3, we have to, this is our something has to be greater than 0. Okay, so if you solve this inequality, you get x greater than equals to 3, and this can be written in the interval form 3 to positive infinity, and here you get x greater than 3, which in interval form comes out to be 3 to positive infinity. I hope this is clear to you all. So now if this is clear, then let's take a question, and this question was asked in J-means. It's a PYQ of J-means. So we have fx is equals to 1 upon square root of x square, greatest integer of x square, minus 3 times greatest integer of x minus 10. Okay, now before we get into solving this question, I want to recall the concept of greatest integer function that you all must have studied in your 11th standard. Okay, and 12th standard students, they must be knowing this. So when we have greatest integer function, then how do we define? Okay, so there are two ways. Now if the quantity that is present inside the square bracket, here it happens to be x. Now if x is an integer, then this will come outside the square bracket as it is. What if x is not an integer? Then in this situation, we get immediate integer lying to the left of x, on number line. Okay, let's understand this with an example. Like if I take 5, okay, so as per the condition that we have studied, when the quantity inside the square bracket is an integer, it comes outside the square bracket as it is. And when we have like a non-integral number, let's say we have 7.3. So when we have 7.3, just have a look on the number line. So number line, here we have 7, we have 8, and let's say we have a 6 over here, and 7.3 will lie somewhat here, I think. Yes, 7.3. So when we have a non-integral value in the square bracket, then we have to search for the immediate integral value that lies to the left of that non-integral value. So in this case, 7.3, the immediate integral value is 7. So we'll write 7. Okay, I hope you all understand. So if you understand this, now this question becomes very easy for you all. And just we have solved the square root function. Okay, so this structure is like quite similar to 1 upon square root of something. And when we have the square root function in the denominator, and if we want to define it, because we want to find the domain, for domain we have to define our expression. Okay, so if we want to define this expression, we have to make sure that something is greater than 0. Now our something in this case is greatest integer of x square minus 3 times of greatest integer of x minus 10 greater than 0. Okay, so just for simplicity, because this expression is looking quite complicated, because we have greatest integer and we have a square bracket. So let's say greatest integer of x is equals to t, so that we can factorize it in a simple manner. So we have t square minus 3t minus 10 greater than 0. Now you all must have studied middle term splitting method of factorization in your earlier classes. So using that method, if you factorize this, we get t minus 5 into t plus 2 greater than 0. Okay, so now what? Now what is our requirement? We want this expression to be positive, isn't it? Okay, we want this expression to be positive. So we have a method called wavy curve method. So if we draw the wavy curve for this expression, t plus 2 into t minus 5. Okay, so the critical points for this expression are what? Critical points. How do we get critical points? When we plot wavy curve, all the linear factors we equate to 0. So when we equate t plus 2 is equals to 0, we get minus 2. And when we get t minus 5 is equals to 0, we get 5. So on the number line, we'll mark minus 2 and then mark 5. Now the wavy curve will start from the rightmost of 5 with a plus sign, then it will go alternate negative and then positive. So wavy curve is not the exact curve for the expression. Okay, wavy curve only tells you when your expression is positive, when it is negative, and when it is equals to 0. So when your curve intersect the number line, so at these point, this expression achieves 0 value, and to the right of 5, as you can see, this expression is always positive, and to the left of minus 2, this expression is again positive, and in between minus 2 and 5, it is negative. So we want t minus 5 into t plus 2 positive. So for positive, we have this region. Okay, so this region is positive, as well as this region is also positive. Both of these regions are positive. So we'll write this is positive for t less than minus 2 or for t greater than 5. But our actual expression, as you can see, our actual expression is what? It has the variable x. So we have done a substitution here just for solving the inequality. So again we'll back substitute. Okay, because for domain we have to find the interval or the values that satisfy our constraint. So that has to be in terms of x. So again we'll write greatest integer of x less than minus 2 or greatest integer of x greater than 5. Now we'll solve this inequality using number line. Okay, so let's draw the number line. Okay, I need a quite larger area for writing, because that will help you to understand things very clearly. So let's draw the number line, and I am solving this one, greatest integer of x less than minus 2. Now let's plot minus 2 here, and the close proximity of minus 2 we have integers minus 1 and we have minus 3. Now we have to search for those values of x in such a way that if we take the greatest integer, then it should be less than minus 2. So let's start from minus 2. If we take minus 2, then minus 2 is equals to minus 2 by the definition of greatest integer function. But we want greatest integer of x less than minus 2, so this is not satisfying. Okay, what if I search for some value of x in this region? Okay, if in this region, let's say I take minus 1.999. Okay, if I take minus 1.999, again I get what? I get minus 2. So but I want something whose greatest integer is less than minus 2, so again this is rejected. Now what if I take some value from this portion? If I take, let's say, minus 2.1, this is your minus 2.1, roughly minus 2.1. So if I take minus 2.1, its greatest integer will be minus 3, and minus 3, it is less than minus 2. So this condition is satisfying here. Okay, so all the values of x that lies to the left of minus 2, they are satisfying this constraint. So this constraint is getting satisfied for x less than minus 2. Got it? Okay. Now let's come here. So here we have greatest integer of x. It has to be greater than 5. Okay, so let's mark 5 on the number line, and then you plot some more integers, mark some more integers in the close proximity of 5, like you have 6, you have 7, on the left of 5 you have 4, plus 4, actually it is plus 4. Okay, it's plus 4, and you have either 3. Now you want x such a way that its greatest integer is greater than 5. So if you take x as 5, let's say you take x as 5. So 5, greatest integer is 5. But we want greater than 5. So this is not possible actually. What if you take something less than 5? Less than 5 means what? Some number from this place. Let's say it is 4.999. Okay. So if we take 4.999, its greatest integer is what? It's 4. So we want something which is greater than 5. So again, this is not possible. What if you take a number greater than 5? So something greater than 5 will be, let's say it is roughly 5.3. So if you take 5.3, again you get 5. But you want something greater than 5, so not possible. Now, if you take 6, okay, so let's see what happens. So 6, greatest integer is 6, and any number which is greater than 6, like 6.1 or 6.2 or 6.33. So 6 point something will again be 6. So we understand by all this calculation that for satisfying this constraint, x has to be greater than or equals to 6. And if we write this in the interval form, we get x belonging to 6 to positive infinity. Okay, so we have x less than minus 2, which in the interval form can be written as x belonging to minus infinity to minus 2. And this inequality is giving us 6 till positive infinity with a closed 6. Okay, so now we'll make the union, because we have OR here, and you all are aware of the difference between OR and AND. When there is OR, we have to take union, and when there is AND, we have to take intersection. So our final answer will be the union of these two solutions. Okay, so x belonging to minus infinity to minus 2, union 6 till positive infinity. This is the domain for our expression. Which expression? This expression. Okay, this one. So I hope you all enjoyed this video. So this was all about today's session, and I did my best to make you all feel comfortable and happy. If you like my video, then please share it to your friends and loved ones, and make sure to subscribe my channel and hit the bell icon to get the notification of my next upcoming videos. See you all, my lovely friends, in my next upcoming videos. More exciting and awesome questions. Till then, bye bye, stay safe, and have a nice day.